Our essential question here is, how do we solve linear inequalities? Well, we solve linear inequalities almost the exact same way that we solve most linear equations. Only our answer is going to be a whole set of solutions. And I'm going to show you that by just graphing a couple of examples here. All right, so here we have, I want to graph x is less than 2, and then I'm going to graph x is greater than or equal to negative 1. And I'm going to just do these on a number line. Okay, so for x is less than 2, whenever we have less than and not less than or equal to, we go to 2 and we draw an open circle around 2 because it can't be equal to 2. And then if we're reading this correctly, x is less than 2, well, in which direction are all of the x's less than 2? Well, that would be to the left. So this is a graph of x is less than 2. Now here in the other example, we have x is greater than or equal to negative 1. So I'm going to go to negative 1, and I've got my circle now. It's greater than or equal to, so it could be negative 1, so I get to fill in this circle. And x is greater than or equal to negative 1. We know it's greater than because it opens up towards the x. So all of the x is greater than or equal to negative 1. These all go off to the right. All right, now we're going to look at graphing compound inequalities. Compound inequalities are of two forms, either and or or. First, let's look at an and situation. It's called an and because we can read it as negative 1 is less than x, and x is less than or equal to 2. And if we were to cut out the x in the middle, it should make sense. Negative 1 is less than 2. Negative 1 is also less than or equal to 2. So whenever we graph this on a number line, it should look like this. Notice that this negative 1 is less than x. This does not have the or equal to. So at negative 1, we're just going to draw an open circle. But at 2, it's or equal to, so it's a closed. And x is trapped in between these two things. So we're going to shade everything in between. Now the or is a little bit more straightforward. We have or right here. So these tails should always go off in opposite directions. X is either less than 3 or x is greater than 5. So if x is less than 3, I have an open circle here at 3. And all the x's are less than 3. So it's all of these numbers less than 3. Or it's all of the x's greater than 5. So an open circle at 5, and all of the x's greater than would go in the opposite direction. Now for a quick reminder before we get into solving, if you divide by a negative, the inequality has to flip. So if I have negative x is greater than 17, this is the same thing. Like if I divide both sides by negative 1, this is the same thing as x is less than negative 17. Okay, now let me show you why that's true with just some numbers. We know that 3 is less than 9. Now, if I were to multiply both sides by negative 1, that would say negative 3 and negative 9. And if I were to keep the sign the same way, then I would be saying negative 3 is less than negative 9, which is not true. It's greater than. So whenever you divide by a negative, flip the sign. All right, so let's jump into solving, and I'm going to jump straight to compound inequalities. So this is an or compound inequality. How would we solve 3x plus 5 is less than 11, or 5x minus 7 is greater than or equal to 23? Well, for this one, you really just solve each of these inequalities, and you do it just like an equation. Only if you multiply or divide by a negative, remember to flip your sign. So here, 3x plus 5 is less than 11. My first step is going to be to subtract 5 from both sides. All right, so now we have 3x is less than 6. Divide both sides by 3. We don't have to flip the sign because we're dividing by a positive, so x is less than 2. Or, on this side, 5x minus 7 is greater than or equal to 23, so I need to add 7 to both sides and do that in a different color. So 5x is less than or equal to 30. Just like solving, I divide by 5. And x is greater than or equal to positive 6. So now I'm going to graph that on my number line. All right, since it's an OR situation, we know that this graph is going to go off in two different directions. We have x is less than 2, so at 2 I have an open circle. It's greater than or equal to 6, so we have a closed. All right, so less than 2, all of the x's less than 2, well 1 and 0, and all these numbers are less than 2. And all the numbers greater than or equal to 6, so 7, 8, 9, 10, all those are bigger than 6. And now I've solved and graphed the compound OR inequality. Now solving an AND compound inequality is a little bit different because you're kind of working from the inside out. You're dealing with two inequalities at the same time, but we're going to focus and we're going to make this like our main piece. Okay? We're trying to get this x by itself. So just like any equation, if I was trying to get the x by itself, my first step would be to get rid of this 7. So I know I need to subtract 7. So I'm going to have to subtract 7 from each side of these inequalities. Okay, so now I have negative 8 is less than or equal to 2x, which is less than or equal to 12. Now here again, I look at just right here in between the inequalities. If I need to get x by itself, I'm going to have to divide both sides, or divide everything by 2. Right, so I'm going to divide the 12 by 2 and the negative 8 by 2. Now here I have a negative divided by a positive. Do I need to flip the sign? No, only whenever you're dividing by the negative. So we have negative 4 is less than or equal to x, which is less than 6. I quickly check myself to see if it makes sense. Is negative 4 less than or equal to 6? Yes. Is negative 4 less than 6? Yes. So now we can graph this on our number line. At negative 4, because it's less than or equal to x, I'm going to have a solid dot. And at 6, it'd be open. And here we have x trapped in between the two of these. So all of the values between negative 4 and 6 are my solutions. Just to reiterate, that means that you could plug in 0, 1, 2, you could plug in a half into this x, and you would get a true statement. Like think about 2. Is negative 4 less than or equal to 2? Yes. Is 2 less than 6? Yeah. All right. Finally, we're going to look at two special cases. Let's say we had 2x minus 8 is greater than 2x plus 1. Well, if I'm trying to get my variables on the same side of the inequality, my first step would be to subtract 2x from both sides. That eliminates, so now I have negative 8 is greater than 1. Now, is negative 8 greater than 1? No. No, this is a false statement. This is false. So anywhere on my number line, there's nowhere I could shade on the number line to ever get a true statement. There's no x value I could plug in to make this ever work. So in this case, there's no solution. Now, if I were to flip this around, and I said 2x minus 8 is less than 1, or I'm sorry, less than 2x plus 1. After I subtract the 2x's from each side, just like last time, I get negative 8 is less than 1. Well, this is a true statement. If I ever get a true statement and all my x's have eliminated, it's just an always true statement. Then that means it doesn't matter what I plug in for x, I'm always going to get a true statement. So in that case, if you had a number line, you would shade everything. And the answer here is all real numbers. And that's how we solve inequalities, linear inequalities. All right, bye.